There seem to be far more computers on the internet than the number of available IP addresses. How is that possible? In this video, I'll talk about the IPv4 address space, the different types of addresses, and how they are used and allocated. Internet Protocol version 4 addresses are 32 bits, but instead of writing them in some form of binary, such as hexadecimal, we write them as 4 decimal numbers, each in the range 0 to 255. This gives us the value of each byte of the address. Within a local area network, we specify how many bits are allocated to the address of the hosts in the net and how many bits are used as the address of the network itself. The addresses in the local network form a contiguous block. They start at 0 in the block. To specify the address space of a local area network, the convention is that we write the network number followed by zeros to pad out the 32 bits, and then follow that by a slash and the number of bits allocated to the network number. That is the network address. So, for example, we might have an address like 192.168.0.0/16. This means a network address of 192.168 and a range of local addresses from 0.0 to 255.255, or, in pure binary, 0 to 16 ones. Or if we write that in a full decimal number, 65,525. So that's the range of local addresses within that block. In a previous video, I described the idea of a net mask. This is a binary number that can be used to mask out the local host addresses, leaving the network address, followed by a few zeros. In the previous example, the net mask would be 255.255.0.0. And if we take any IP address and mask it with that mask, 255.255.0.0, then if the result is 192.168.0.0, we know that the address of the host is inside our local area network. Net masks are very easy to generate from the network description. So 192.168.0.0/16 means the net mask of 16 ones followed by 16 zeros. That's very easy to generate by a program. The full IPv4 address range of 0.0.0.0 up to 255.255.255.255 has over 4 billion addresses, or to be exact, 4,294,967,296. Now, this might seem like an awful lot of addresses, and more than enough to cover all the possible computers we ever want to attach to the network. But unfortunately, the allocation of addresses is not simple. The address range is broken up into a number of standard sub-ranges that are used for various purposes, and this reduces the addresses that are available for normal allocation to hosts. The addresses that are available are then broken into smaller ranges that are allocated to regional network registrars, or RIRs. There are 5 RIRs that cover the world. These regional internet registries are responsible for allocating and registering blocks of addresses for companies and organizations. This includes internet service providers that in turn provide internet connections and addresses to the end users, and they allocate an address to each user from the block that the RIR has given them. The internet registries are one for Africa, one for the US and Americas, the Asia Pacific Network Information Center for that region, a Latin America and Caribbean Network Information Center, and a European Network Coordination Center. Here is a map of the IPv4 address space. You can see it's very colorful. The color codes are all the different RIRs and various other purposes. You can also see some large blocks that are allocated to other purposes. In the early days of the internet, large companies or universities were allocated blocks, and many of these are still held today. Universities such as MIT, for example, have a block of addresses. Several US government departments, such as the Department of Defense or the US Postal Service, also have been allocated blocks, and they hold them today. Two very large blocks are in the upper right of this map. They're the multicast addresses and reserved for future use. Now, I'll come back to multicast addresses later in the video. There are several blocks that are marked private and are designed for use inside a local area network and have no use on the public internet. These are the range 10.0.0.0 with an 8-bit mask. So there are 16,700,000 odd addresses in that block. The 172.16.0.0/12 block, which has 1 million addresses, and the 192.168.0.0/16, which has 65,000 addresses. Now, these are what we call private address ranges, and they are used inside the local area networks. When we use an IP address, we're not actually naming a particular computer. Instead, we're really naming the interface onto the computer. Now, you might think that's a pretty subtle difference, but it means that if a computer has more than one network interface, it will also have more than one IP address. And you can think of the IP addresses as labeling the interfaces rather than the computer itself. You can understand this if you think about the function of a network router. Routers are going to have multiple network interfaces because they connect from the local area network to the external wider internet. And the router will take packets from the local area network and forward them to the wide area network after making some routing decisions and maybe changing the addressing and so on. And you can see that in this diagram. So on the left we've got the local area network, which has its address in the 192.168 range, and on the right we have an address in the wide area network. There are also addresses that are used for special purposes, and these are the all ones, 255, 255, 255, 255. That is a broadcast address and can only be used inside the local area network. It allows you to send out a packet that is received by all hosts on the local area network. There's also the loopback address, the 127.0.0.1. This is completely internal to the computer itself and doesn't appear on any interface. So this one is unusual. It doesn't name a particular interface, it's just inside the computer. We give a name to this. We sometimes call it localhost or sometimes call it home. We can use localhost to run servers that are only available inside the computer and not accessible from outside. So for example, we could run a web server listening on a port that only accepts browser requests from the local machine. And in that case, we'd use the 127.0.0.1 address. In version 4 of the Internet Protocol, the addresses are 32 bits, as I said before, and this gives us over 4 billion different addresses. Seems like a lot, but because of the allocation of addresses to RIRs, the Internet registries, companies, organizations, and all those special purpose ones, then we're starting to run out of addresses. So for example, the Asia Pacific Network Information Center, APNIC, has run out of addresses to allocate. They can't give out any more sub-blocks to anyone. So on the other hand, we have a growing number of devices that need to communicate on the internet. So they need an IP address. With the growth of the Internet of Things, we have tiny sensors, many of these, that need IP addresses. The solution is to switch to a larger address with more than 32 bits. This is exactly what the IP version 6 has done, and they moved to 128-bit addresses. Unfortunately, IP version 6 is taking a very long time to roll out, even though every mainstream operating system implements it and all the current network equipment such as routers implement it. An interim solution to the address scarcity was developed, and this was so successful it seems to be the default, and there's no incentive to change over to IP version 6. The solution is to reuse addresses from the private address ranges. Remember I said there were a number of ranges designated as private? Here they are again, the 10.0.0.0 range, the 172.16 range, and the 192.168 range. If you've ever configured a home router or access point, you'll almost certainly have an address in one of these ranges to use on your local area network. Here's our image of the router again, and you can see the left-hand interface there uses the 192.168 address range. This means all the devices in your home are connected to your local area network using private addresses from a private address block. A huge number of local area networks now use the same private network range of addresses. So there are many duplicate addresses in use. How can that possibly work? Well, the way it works is if a computer wants to communicate outside the local area network, and we're using a private address inside the network, the computer's address has to be translated to a single non-private address outside in the wider network. And this is done inside your router. As I said, the router has two or more interfaces, one for local area network and one for, at least, for the wide area network. And when a node on the local area network sends a message or creates a connection to the machine outside on the wide area network, the router translates the local area source address of the node to a wide area address of the router, and also translates the port number to a new unused port number. So here, if we look at this image, you can see that the original address on the left there, the 192.168.1.100 with port 1234, if a packet comes in from that address into the router will translate it to the router's address here on the right, 120.23.45.1, but a new port number. And it keeps a table of these translations, these port number translations and address translations, so that when a reply comes back to that particular port number, it knows that it maps onto the original source. So it keeps a table internally, and it can look that up when packets come in. Essentially what's happening is we're using the port number to give us more bits in the address. This technique is called Network Address Translation, or NAT, N-A-T. I said earlier that a large block of addresses, over 268 million, are reserved for multicast addresses. Now, most conversations on the internet are between one source and one destination computer. We call this unicast. Think of, say, a request by a web browser to a web server. You have your one entity on one side, the web browser, and you have one entity on the other side, the web server. Another example is sending email. You send email from your computer to a mail server. So these are unicast or one-to-one transmissions. We can also have broadcast addresses. So within a local area network, but not on the wide area network obviously, you can have broadcast addressing using this special broadcast address either at layer 1, for example Ethernet frames, or layer 2, UDP packets. And we can use the 255, 255, 255, 255 address for broadcast. But there's another form of addressing, and this is multicast addressing. This happens on the wider internet, where it's possible to send UDP packets from one source machine to many destinations. And this is what we call multicast. You can see here in this diagram, our source is sending it to a number of destinations. The one packet goes out to a multicast address, hence the block of addresses, and all those destinations are connected to that one multicast address, so they'll get a copy of the packet when it comes in. A full description of how multicast works is too complex for this video, but basically it's done by routers accepting requests from potential receivers to join a given multicast address through a tree. Now this tree is simply a data structure joining all the destination receivers via routers. So you can see here it looks a bit like a tree with a root at the bottom, and each receiver will request of the router that it be allowed to join a particular multicast address. Going the other way, the source sends out packets to the multicast address, and the routers duplicate the packets where there are new branches of the tree attached. And eventually that one packet is copied all the way to all the different receivers. The tree is built using a control protocol called the Internet Group Management Protocol, or IGMP, and it's used for routers and clients. So in this video I've described the IPv4 address space, the different types of addresses and how they're used and allocated. I covered the use of private addresses and the concept of network address translation, very important for conserving public addresses. And I also introduced the idea of IP multicast. I plan to do more videos like this on other aspects of the network, so please subscribe, and thanks for watching.